Hi class, we're going to start the tutorial number 9 for Applied Science 248. Okay. Actually, I'm going to start with example number 2. So for example number 1, it's just basically connects the dot between single integral, double integral, and triple integral. Okay, so you'll get a sense of what's the connection there among these integrals. Okay. Yeah. Okay, so let's start from second example. Same example here. Okay, what it asks is trying to ask you to give a region or a domain D, okay, such that it minimizes the value of a triple integral, and the triple integral is this. Okay, so the question is asked is what kind of a D will minimize the value of this triple integral, right? All right, so basically we need to look at this question. We need to look at this question from simple properties of a triple integral. Now, if you remember that when you look at the triple integral here, the integrand here, okay, the integrand is f of x, y, z, okay, equal to 4x squared plus 4y squared plus z squared minus 4. So that's the integrand here. Okay. Now, for any integral, essentially, okay, if this integrand is greater than 0, then the whole integral, of course, is going to be greater than 0, right? So it's just similar like a single integral, right? And if you're integrating from a to b, okay, let's say from a to b there, and this is your f of x. So if this f of x is greater than 0, right, in this case, and apparently the area that you obtained is also greater than 0. Okay, so if fx is less than 0, then you obtain a negative value of area, right? So similar idea here too. If this is greater than 0, then the whole integral will also be greater than 0. But if this is less than 0, right, and it'll be also less than 0, the triple integral. But the problem is what decided or what determines the value of this integrand to be less than 0 or greater than 0, right? And that basically comes from the region D. Okay, so the domain D or the region D determines the value of this integrand f of x, y, z. Okay, yeah, and we wanted to minimize this guy here, and apparently what we want is we want a domain, or we want a region D, okay, such that the whole thing is less than 0 or negative. Okay, so this region D, right? This region D should give, okay, should give a negative, okay, f of x, y, or in other words, you want this one to be less than 0. Okay, you want it to be less than 0. If this is less than 0, okay, then apparently it's minimized for the triple integral. Okay. Well, okay, so what does that give us? If f of x, y is less than 0, and that basically, right, give us 4x squared plus 4y squared plus z squared less than 4, right? Okay, and this is basically it's a range, right? It's a range here, right? And the range here tells you for x, y, and z, okay, satisfy this less than 4. Okay? And as a matter of fact, and this is basically, okay, the region D that you're looking for. Okay, if you use a maple to sketch this inequality here, okay, so the equal sign here basically will give you this surface, okay, which is like a football, right? Less than 4, the less sign here basically what's inside this thing, this surface here. So the whole thing here, right, less than 4, will give you the region D. Okay, will give you region D. Apparently, if you pick any point, right, inside this region D here, and you get to this whole thing less than 4, which is basically your integrand less than 0. Okay, yeah. So this is basically the region D you're looking for. Okay. Okay, so that's the first example there. This example here should help you actually in one of the assignments. Okay, that assignment question is ask a region so that you can maximize that triple integral. Okay, okay, let's take a look at the second example here. Is a changing order of integration. This example, as a matter of fact, we done it in the lecture. Okay, so in the lecture, what we did is that we wanted to calculate. Okay, calculate the volume. Okay, between paraboloid. Okay, so calculate volume of dz equal to x squared plus y squared, and z equal to 4 minus x squared minus y squared. So in the lecture we did this part. Okay, so we actually did it using polar coordinates, if you recall that. So this is basically the region D we're looking at here. Okay, the blue color surface, okay, is z equal to 4 minus x. Okay, so the blue color surface is this. The green color surface is z equal to x squared plus y squared, the paraboloids. Okay, yeah. So the volume of this, but in this question here, I'm not going to calculate volume. But what we want to do is, in that particular case, let's check out to do this if I use a different order of integrations here. Okay, yeah, integrations. Okay, the first one is what we did in the lecture. Okay, so if I integrate use with respect to z first, and then y, then x, right? So in that particular case, if you remember, you draw this is Cartesian coordinate. You draw an arrow lines in the z-axis direction first, okay? And the first contact, second contact, give you z mean and y mean, right? Yeah. So in this case, the v, okay? So dz, dy, dx. So z mean here is x squared plus y squared. So that's the first contact. And second contact is this. Okay. And the y and x is when you look at the shadow here, right? The shadow. Okay. So first draw a arrow lines in turn the y-x direction. This is y-axis, so y-x direction. So the first contact, okay, give you the y mean, okay, which is negative 2 minus x squared, and positive 2 minus x squared. Okay, yeah. Hang on a second. Is what's going here? Just a second here. Oh yeah, that's right. Yeah, the circle here, right? This circle here is x squared plus y squared equal to 4. Okay, the circle. Then x value, okay, from negative square root 2 to positive root 2. Okay, so this is what we did in the class. Okay, but now what I want you to do is let's try this order at here. Okay, dx, dz, and dy. Okay, okay. So if I want to try this order here, right? Yeah, if I try this order here, then what we need to do is we need to. This is x-axis. We need to draw an arrow lines in the x-axis direction. Okay, so apparently, so what we're gonna draw is right. You draw an arrow lines in the x direction. So let's see. I'm gonna draw it in this direction here. Okay, there, right? So that's one arrow line here. Okay. Well, but you got to be careful here. You see, when you do this order of integration, you can see that is you have a top portion and bottom portion of the egg. So if you draw it at a different location, if you draw this location and then you draw this location here, you can see that your contact point, right, give different values. Okay. So when I draw it to the upper portion of the egg, okay, your x min and x max is here. When you draw the lower portion here, your x min and x max is here. So they're different. They're different. Okay. So in this particular case, right, we're gonna have to do it piecewise, basically. Okay, you're gonna have to do it piecewise. Yeah. So piecewise means we separate this region, this whole region D, or whole egg, into two portions. The first portion is D1, second portion is the D2 at here. Okay. Yeah. So basically, we're gonna talk about have V equal to D1, okay, dV plus D2. Okay, and dV, okay, something like this. Okay, so you're gonna have two triple integrals, okay, dx, dz, dy. Okay, yeah. So let's take a look at the first region D1 and the D2, right? So what would that give us? Okay. Yeah. So D1 is here. Okay. You draw an arrow line in the x-axis direction. Your first contact is here, and second contact is over here, right? Yeah. So apparently, the upper portion of the egg is given by this. Okay, given by this. Okay. So in other words, you can rewrite this x, right, square is equal to z plus y squared minus 4, right? Minus 4. Okay. So x equal to positive negative z plus y squared, okay, minus 4. Oh, I'm sorry. X squared is negative here. So what are we talking about here? So this actually. Okay, this is actually 4 minus y squared minus z, right? Yeah, x equal to positive negative 4 minus y squared minus z. Yeah, and where do you take the power negative? Negative for this portion here, right? This side here is negative, and this side is positive. Yeah. Okay, so x, right, goes from negative 4 minus z minus y squared to positive square root z y squared. So that's your x limits, x min and y min. Okay. So for z min z max or y min y max, right? So these two, you're gonna have to look at the shadow of this solid, right? And the shadow of the solid in which plane? In the yz plane, right? In the yz. So project that, right? Project that in the yz plane. Okay. So if I project that in the yz plane, okay, so let's see. So let's see what do I have here, and let's look at the projection. So this is y and z plane. Okay, and what we're gonna look at here is we're gonna look at basically. It's going to be something like this, okay? Something like this. Yeah. So there's an egg and jointed at this location. Okay, so this location here is 2. So what we're integrating here is in the z first, okay, and then y. So this is your shadow, okay, in the zy plane. So I guess we need to draw an arrow line, okay, in the z axis direction, okay. And since we are integrating separately with respect to d1 and d2, okay, so you actually need to draw 2 arrow lines, okay. One arrow line, so let's redraw that. Okay, so one arrow line is just, you know, across this d2, okay, and the other arrow line across this D1 upper portion, right? Or maybe we don't call it D1, D2 here, because there's a shadow here, right? So maybe we'll call it R2 and R1 at here. Okay, yeah. Okay, so apparently for D1, this one, or for the R1 here, right? So your Z value, the first contact is here, which is 2, mean value, and second contact, which is the max at here, right? And that's basically your Z max. Okay, Z max here, right? If we project that into the xz plane, okay, so this is the 4 minus y squared over here, right? So original one here is z equal to 4 minus x squared minus y squared. So when you project that into yz plane, so the x value is 0 now. So this is basically where it comes from. Okay, z equal to 4 minus y squared. Okay, right? So that's your max there. And then y value is you sweep these arrow lines across the whole region, okay, and to find the mean of these two at here, okay, and which is square root negative square root 2 to positive square root of 2. Okay, so that's the limits over there. That's the limits over there. For this portion in here, right? For this portion here, for the D2, for x value, x range, okay, so what we do is you draw an arrow line in the x direction here. First contact give you x mean, second contact give you x max. So x here is from this surface, so that's positive negative z minus y squared, right? So x mean, x max basically goes from negative z minus y squared to positive square root z minus y squared. Z value, xy value, z value, y value, that you look at the shadow, right? So basically the bottom here, R2, that's the shadow. And you draw an arrow line in z x direction, you're talking about z next. So this first contact give you z mean, second contact gives z max. So z max is 2. And z mean here, right? Z mean here, that's basically when you x is equal to 0, so we have z equal to y squared, so y squared at here. Okay, and then you sweep this arrow lines across the whole region R2, so you get y mean and y max. Okay, so that's basically the setup when you do this in the order of dx, dz, dy. So apparently this order of integration seems to be much complicated than the order of dz, dy, and dx, right? So sometimes the order of integration does matter. Okay, it does matter. Okay. The other order of integration, you can take a look at it. I think would be pretty much the similar thing. Okay, so you can take a look at the tutorial notes regarding this integration order. Okay. Yeah, so I'm not gonna spend too much time here. Okay, let's talk about the example number 4. Okay, so for this example here, you are required to calculate the triple integral. So the triple integral here, what you're required to is to find, let's see, find a volume. Okay, find a volume of region D. Okay, yeah. So what's the region D here? Region D is bounded. Okay, region D is bounded by a cylinder. Okay, cylinder here. Okay, and a top surface right here. Now this top surface is intersected by a surface z equal to x squared plus y squared with the cylinder. Okay, so the cylinder is described by this, okay, in Cartesian coordinates, and the top surface is described by this one here. Okay, this is basically a paraboloid, right? It's paraboloid, and we're looking for the volume of this, or the triple, to set up the triple integral, right? Triple integral here. And then of course, if just ordinary normal integrals, triple integrals is fine if you have an integrand there. Okay, Let's take a look. The question here is actually more of exercise for polar coordinates. Okay, and why do you use polar coordinates? The reason is because your projection of the solid region D in the xy plane essentially gives you a circle, right? Yeah, give you a circle there. Okay. Okay. So how do I do this? Okay. Number one step is always okay. If you want to use the polar coordinates, then you have to convert everything into polar coordinates, right? But this general steps, right? The general steps is you draw an arrow line, okay? Of course, let's see. Okay, well, I wanted to integrate in this order. Okay, dz, dr, and d theta. And you integrate it with back to z first. So your step number one is to draw an arrow line in the z-axis direction. Okay. Find the z limits, right? And find z limit. Okay. So your first contact with the solid region D will give you z mean, and second contact with the solid region D will z max. So apparently z mean is 0, and z max, right, is the top surface here. Okay, top surface is z equal to r squared x squared plus y squared. Okay, but we don't want x, y, we want everything turned r. So you replace this x and y, right, with r cosine theta and r sine theta. Okay, so that's basically where the r squared is from, right? So that's the top surface is, okay, in cylindrical coordinates. Okay. And then we project this whole solid region D into xy plane. You get a circle, okay, right? You get a circle. Basically, it's the bottom of the cylinder. And when we draw a reading lines across this shadow, that's called L, right? Then the first contact between this reading line and the shadow is the R mean. The second contact give you the R max. Apparently, R mean is 0. So the question is, what about R max, right? R max. Well, as a matter of fact, we did such kind of exercise for finding R mean and R max. Okay. Yeah. One simple approach is R mean or R max can be obtained from the polar coordinates. Okay, polar coordinates. So you look at this bottom circle here, right? And if we replace x and y with r cosine theta, r sine theta, you basically get a polar equation, r equal to 2 sine theta. And that actually describes the circle here, right? So for every point on the circle, you have r equal to 2 sine theta. So that happened actually just to be your r max, right? R max here. So R mean is 0, and R max, okay, is 2 sine theta. Okay. Otherwise, what you can also do is, you can also look at the shadow, okay, in xy plane, okay, like this, right? So this is your x-axis, your y. So this is your shadow here, right? It's your shadow here. So what we did is we draw arrow lines across this shadow here. So what we're looking for is this distance here, this distance. That's your R max, right? And this is your theta. Okay, this is your theta here. So the whole thing here is 2, right? So how do I get the R? And if I connect these 2 points here, I get a right triangle. So this is theta. So basically this is theta here. So apparently this R max, right, equal to 2 sine theta. There. So that's how R max is obtained here. Okay. Yeah. Okay. So Z mean Z max, R mean R max obtained, and in the end you find theta mean theta limits. Okay. So for theta limits, you sweep this or rotate these reading lines across the whole shadow, okay, and find the mean and max angle that includes this whole shadow. So apparently in this case theta mean is 0 and up to over there, which is pi. Okay. So now you can set up the triple integral. Okay. So the triple integral here three integrals here. Let's say suppose you're calculating the volume. Okay, so in terms of cylindrical coordinates, it's dz, rdr, and d theta. Okay, and dz we find limits is from 0 to r squared. Okay, and r we find the limits is from 0 to 2 sine theta. Okay, and theta is from 0 to 2 pi. Okay, so this integral here is very easy to calculate. Okay, you can calculate that. So try it out. Okay, if there is a certain kind of integrand here, right? So we're gonna replace the x with r cosine theta, and the y with r sine theta, and z is kept the same. Okay. So that's basically a general approach for triple integral now. Oh, sorry, this is not pi, 2 pi, this is pi, right? Let me see, this is pi here. Okay, so that's the this example here. So let's take a second example, the last example. So for the last example here, for this example, and we are looking for triple integral of using the spherical coordinates. Okay. Yeah. So this time, let's see, we calculate the volume of this solid region D shown in here. Okay, let's see what kind of a region D do we have. Okay. So this region D is bounded by two surfaces. One surface is this, and the other surface is this. Okay. Now, if you recall in the last lecture, for this particular surface, right, that's basically the surface of a cone. Okay, it includes a cone, so you can see that there are a certain straight line here represent the cone here. Okay, and the bottom surface, this one here. Okay, that actually is a sphere surface. Okay, so for this one here, this is the spherical equation in spherical coordinates, but if I write that in Cartesian coordinates, it's x squared plus y squared minus z minus 1 squared equal to 1. Okay, so that's a sphere with origin of the center of the sphere at 0, 0, 1. Okay, with the radius of 1. So you have two surfaces, and we're looking for the volume between the two surfaces. Okay, the two surfaces. Now, in spherical coordinates, okay, the equation for the cone, if you remember that, is pi equal phi equal to pi equal phi equal to pi over 4, right? And we did that in the class. Okay. Okay. So how do I go with spherical coordinates? So come back to the procedure. Basically, first step is starting from origin. You draw an arrow line across this whole region D, right? Across the whole region D. First contact between the arrow line or the reading line is your rho mean. Okay. And second contact give you the rho max. Okay. So basically, let's put down the triple integral setup. Okay. So your integrator is 1 because we're talking about the volume. Okay. And your triple integral setup is rho squared sine phi. Okay. D rho, d phi, and d theta. Okay, d rho divided theta. So that's basically the setup here. So the first thing is we integrate with the rho, so we're looking for rho mean and rho max. And we said the reading line here, starting from origin, first contact give us the rho mean. Second contact, right, give us the rho max. Second contact is the contact between the reading line and the outer surface, which is a sphere, right? The sphere. So the sphere is rho equal to 2 cosine phi. So that's why the rho max is 2 cosine phi here. Okay, the rho max. Okay, so that's how you get 0 to 2 cosine phi here. Okay. Okay, so now you get rho limits, and next one you try to get is phi limits. Phi angle is defined between z-axis and the reading line M. That's phi angle. Okay, and remember phi angle is a range. Okay, maximum and minimum is between 0 and pi. Okay, so how do we get at the actual phi min and phi max? Okay. And if you remember that, it's basically what we do is we start this reading line from phi equal to 0 and then rotate that to phi equal to pi and find during this rotation what would be the phi min and phi max that includes this whole region D, right? So apparently if I use this, if this arrow line is drawn over here, right? So that's where the reading lines first to include this region D here. And this angle, right, it's basically the angle for that cone, which is pi over 4. So that's basically your phi min, pi over 4. And if you keep rotate, right, keep rotate until it includes the whole sphere, and basically you end up with at the xy plane. Okay, so that means the phi limits, right, is phi max, okay, is to pi over 2. Okay, pi over 2. Yeah. So that's phi max. Okay, yeah. Okay, so the last one is the theta angle. So theta angle is defined as between the x-axis and the projection of this reading line in the xy plane. Okay, if this is L and projection here, so that's your theta angle. Okay, a theta angle is defined from the x-axis to the projection line L, reading line L. Then you sweep this reading line L across this whole shadow of this region D in the xy plane. Okay, find the min and the max for the theta angle that includes the whole shadow. So in this particular case, it's very simple. So it's 0 to 2 pi, right? So that's the theta angle for the based on this region D here. Okay, yeah. So now your whole triple integral is set up, and you are ready to do this triple integral. Okay. Now, if I carry this triple integral out, let's see what we have here. Okay, so first you're integrating this back to rho, right? Okay, so this rho square here, you consider sine phi as constant, and rho square, the integration come out to is so you come out to is basically 1/3 rho cube. Okay, and that changes from 0 to 2 cosine phi, okay, and multiplied by sine phi, and d phi d theta. Okay, so and this term you calculate that. Okay, you end up with 8 over 3, 0 to 2 pi, and pi over 4, pi over 2. Okay, cosine phi cube, sine phi, d phi d theta. Okay. Okay, so now you integrate this portion here, and it's just going to be a simple substitution rule for this integration. Okay, for this integration. Okay. Yeah. So if you wanted to write here, so that's d cosine phi, and there should be a negative, and d theta. This is cube. Okay. Okay. So what do I get? 0 to 2 pi. Okay. For the internal integrand, and we have the results of cosine to the power 4, phi over 4. Okay. And then you let phi go from pi over 4 to pi over 2. Okay. And d theta. Okay. Yeah. So the whole thing here, okay, you end up with basically, because what's common is a scalar value, okay? And so basically pi, you'll get 1 over 16, okay? And this whole thing is 2 pi, okay? So overall you're gonna move into just pi over 3. Okay, so that's how you get this one using spherical coordinates. Okay. Okay, so I hope this video helps, and let me know if you have any questions. I didn't cover all the aspects of the video of this tutorial number 9. You can you still resort to the tutorial notes on the APSC248, okay, especially the first one there, just to check out the connection between single, double, and triple integrals. Okay, thank you.